Hi, I'm Ryan Baker, and this is Big Day in Education. Today we're going to talk about one of my favorite things on the planet, cross-validation, and one of my least favorite things on the planet, overfitting, which cross-validation helps you assess if you're doing. So today will be a fun day for me. I hope it'll be a fun day for you too. Overfitting is when you fit to the noise as well as the signal. So in other words, is your model actually any good at all, or are you fitting to noise? When you look at the graph on the left, you can see a good fit. There's some noise, but you get a line that cuts across them. When you look at the graph on the right, you see overfit. We're fitting to every single point and kind of even dipping up and down when it really probably doesn't make any sense. The model that's overfit will be less good for new data than the model that's a good fit because it's fitting to the signal, not the noise. To reduce overfitting, there's a few things you can do. You can use simpler models, for example, ones with fewer variables. BIC and AIC get to this, as we talked about last week. This is kind of the idea of parsimony, or Occam's razor. You can also use simpler models in terms of using less complex functions, which corresponds to minimum description length, which is something I'm not talking about in the rest of the class, but it's worth taking a look at it. These are kind of the two big ways to get towards reducing overfitting. Can you eliminate overfitting? No. Every model is overfit in some fashion. I'm sorry to tell you, everything you ever do in data mining will be overfit. But you can do things that are less harmfully overfit and less overfit. The question is, how bad, and what are you overfit to? To assess generalizability, you can ask, does your model transfer to new contexts? Or is it overfit to a specific context? The way I like to think about controlling overfit is in terms of assessing generalizability. Does your model transfer to new contexts, or is it overfit to a specific context, whatever that context is? So one way to look at generalizability is just to have a training set and a test set. You take your data and you split it into a training set and a test set, usually with the training set being a good bit bigger than the test set. This is good. Your models test on unseen data, but it uses your data unevenly. Some data points are training points, and some data points are test points, and never the two shall meet. Cross-validation is an alternative where you split data points into n, in this case 6, equal size groups. So we've taken our 54 data points and we split them into 6 groups of 9 apiece. So in cross-validation, you're going to train on all the groups but one and test on the last group for each possible combination. So we're going to take the 5 blue groups, we're going to train on them, and then we're going to test on the red group. And then we're going to change which one's the red group. And we're going to train on these 5 blue groups and test on this red group, and so on for all possible combinations. How many groups do you want? We talked about this briefly earlier in the class. You could do k-fold, where you pick a number k and you split into this number of groups, like the case before was 6-fold. Or you could do leave out 1, where every data point is its own fold, and you repeatedly train on every data point except for one, and then test on that one. Which one's better? K-fold is quicker and is preferred by some theoreticians. Leave out 1 is more stable, and it avoids the issue of how to select folds, which lead to stratification issues, which I'll talk about in a minute. The big thing is that when you use leave out 1, you don't have to think about how you select your folds. But when you use k-fold, you really do, and different choices in how you select your folds can have big differences in terms of goodness. So there's a bunch of cross-validation variants. First one is flat cross-validation. In flat cross-validation, each point has equal chance of being placed into each fold. You'll also just see flat cross-validation called cross-validation. Stratified cross-validation, by contrast, biases fold selection so that some variable is equally represented in each fold. Typically, and kind of by default, it's the variable you're trying to predict, but it can also be some other variable that you think is some kind of important context. For example, in Mike Salpedro's work to predict student science inquiry skill, he stratified based on how much the student worked in the simulation and actually discovered that his models were doing very well if there was a lot of student data, if the student was doing a lot of work in the simulation, but they weren't doing so well for more minimal data. And he was able to actually then build a separate model for those cases and show that that led to better overall prediction. Another variant is student-level cross-validation, where folds are selected so that no student's data is represented in 2 folds. So in other words, a student is at any time either in a training fold or in a test fold. This allows you to test model generalizability to new students, which is often something we want. By contrast, flat cross-validation or even stratified cross-validation can just test model generalizability to new data from the same students. Think about it. Do you want to build a model that'll work on new data from the same kids you have data on? Or do you want to build a model that'll work for entirely new kids? Usually we want to build models for entirely new kids, and for this purpose, student-level cross-validation is important to do. Oftentimes a model will look great for flat cross-validation, but will completely bomb on student-level cross-validation, and if your goal is to work for new students, you better pay attention to that. Student-level cross-validation is usually seen as the minimum cross-validation needed in the Educational Data Mining Conference. Papers that don't pay attention to this issue are usually rejected. It's okay to explicitly choose a different cross-validation scheme and discuss that choice and defend that choice, but it's not okay to just ignore the issue and do whatever's easiest. And this becomes an issue especially if you're using tools like Weka that don't have support for student-level cross-validation. Weka's great, it's great for a ton of stuff, it just doesn't have this. It's easy to do this, by the way, with batch-X validation in RapidMiner. Other levels are sometimes used for cross-validation. You'll see lesson or content level cross-validation. Does your model work on new content? School level cross-validation. Does your model work on kids from new schools? Demographic level. This one you don't see very often, but my group is starting to play with it. And we've actually seen that when you cross-validate at the urban, suburban, and rural levels, models tend to work a lot better going across urban and suburban than they do when they're going from those to rural. That's a big important difference to pay attention to if you want your models to work on every kid. And finally, a variant of lesson or content is software package. Can your model even work on completely new learning systems? In some cases it can. The important consideration is, where do you want to be able to use your model? Do you want to be able to use your model on new students, on new schools, on new populations, or on new software content? However you want your model to generalize, be sure to cross-validate at that level. Because if you don't and you ignore this issue, you might have a model that doesn't work nearly as well as you think it does in the case you're using it. And that's a problem. So in the next lecture, I'm going to talk more about generalization and validity and kind of talk about it at a more theoretical level. I'm Ryan Baker, this is Big Day in Education, and I hope you had fun today, because I did. Thank you.